Compare and contrast primary and secondary active transport. In contrast with passive transport, in which materials are moving down their concentration gradient, and so the driving force for the movement of materials across the membrane is going to be the concentration difference across the inside versus the outside of the cell, and that's going to allow for passive transport. In active transport, we are generally going to be moving things against their concentration gradient, and so moving things from low concentration to high concentration. And so active transport is basically a process that is going to build up that concentration gradient that is going to allow for that passive movement or that diffusion to occur. Now, in active transport, because we are moving things against their concentration gradient, we need to add energy into that process. And that energy is going to be in the form of an ATP molecule. And so we need to use energy to build up the concentration gradient. And so, again, another analogy for different transport mechanisms, having a boulder on top of a hill and allowing that boulder to roll down the hill would be an example of passive transport. Passive movement, force of gravity is moving that rock down from the top of the hill to the bottom of the hill. Active transport in this analogy would basically be putting the energy in to roll that boulder back up the hill. So putting it up in that higher position is similar to building up a concentration gradient. And so a classic example of a biological primary active transport is taking a look at our sodium-potassium ATPase. So in this slide, we've got the phospholipid bilayer. We've got a protein complex here, which is our sodium-potassium ATPase. It's a pump that burns ATP. That's what the ATPase portion of it is. And it is going to be moving both sodium and potassium against its concentration gradient. What we're going to see is that, like facilitated diffusion, the protein that's going to be allowing for the movement of the materials or controlling the movement of materials across the membrane are going to have multiple configurations. We're going to have a configuration that is going to be open to the outside. Open the outside over here, and we're going to have a configuration that is going to be open to the inside. And so taking a look at sodium-potassium ATPase as an example of primary active transport, in one configuration, we're able to take sodium from its relatively low concentration inside of the cell. 3 sodium ions are capable of binding to our protein here. Once this is bound, we're going to result in a shape change, which is going to move these sodium ions into that outward position. The transmembrane protein is now open to the outside. We are going to release the sodium outside of the cell. So we built up the concentration gradient, moved sodium from low concentration to high concentration, and then on the reverse movement of this sodium-potassium ATPase, this transmembrane protein, we're going to bind to 2 of these potassium ions. We're going to use ATP in the form of energy that is going to power this shape change, which is going to force these 2 potassiums into the inside of the cell. So we get ATP that is used up in the process, indicates that it's primary active transport. And in this instance, we've moved 3 sodium ions with its positive charge outside of the cell, and we've taken 2 potassium ions with its 2 positive charge and brought it inside of the cell. And so in this case, we are basically moving more positive charges outside of the cell than inside of the cell. So we're building up a electrical gradient. We're moving sodium over here from inside of the cell to the outside of the cell. So we're building up the sodium gradient, and we're taking potassium, which is at a low concentration outside of the cell, and building up that concentration inside of the cell. So in this case, the ATP is directly driving this process, directly powering this process. Now, secondary active transport is similar to primary active transport, but it's a little bit more complicated. Active transport, again, is going to use ATP energy or some type of energy to be a driving force. And secondary active transport means that we're going to use basically the gradient that we established using our sodium potassium ATPase and burning up ATP to power the process. The secondary active transport is going to be using our gradient established by the sodium concentration outside of our cell to result in the movement of other materials inside of the cell. And so secondary active transport is going to start with building up that concentration gradient. And so we've got primary active transport, as we talked about on that previous slide. So that's basically what we've got right here. So using ATP to pump sodium ions outside of the cell, build up that concentration gradient so that there is going to be a driving force that is going to try to push the sodium ions from outside of the cell back inside of the cell. And so what we've got with this transport molecule here, a carrier molecule, is the fact that sodium is going to be moving down its concentration gradient, and the movement of sodium down its concentration gradient is going to provide the energy, to provide the driving force for the shape changes within our molecule here. So as sodium is moving down its concentration gradient, it is going to be driving a shape change, which is going to have the effect of taking glucose and moving glucose, again, against its concentration gradient into the inside of the cell. So in this case, ATP is not driving the process directly. ATP is establishing the concentration gradient, and it's that concentration gradient that is driving the process of secondary active transport. So one molecule is moving down its concentration gradient, and it is basically dragging another molecule with it. In this case, it's dragging a glucose molecule that is interacting with a different portion of this transmembrane protein to move it across the membrane. Now, two terms that are often used when we're taking a look at active transport is antiport versus symport. Symport basically means the materials are moving in the same direction. So over here, we've got both sodium and glucose moving from outside of the cell inside of the cell. With antiport, we're looking at the materials moving in opposite directions. And so if sodium is being moved outside of the cell, potassium is moved inside of the cell. So they're moving in opposite directions.